Here are the notes for section 7.2, deals with comparing two proportions. So objectives, test a claim about two proportions or construct composite intervals. So essentially are the two populations similar, the same, things like that. So just a couple notations. P1 is the population proportion, N1's size, for population 1, so P1's the population proportion, N1's the size of the sample, X1 number of successes, we got P hat is the sample proportion, Q hat is the complement, so these two have to add up to 1. The corresponding notations with the subscripts is 2 apply for population 2, so P2 is the population proportion of the second group, so on and so forth. We also have this pooled sample proportion. So the pooled sample proportion is denoted by P bar, is given by P bar is X1, X2 over N1, N2. So the total number of successes divided by the total number of in the sample. So our requirements are from two simple random samples that are independent, meaning one group does not affect the other group, at least 5 successes, 5 failures. So our test statistic is the z-score. And here's our formula for it. And then so P hat 1 is X1 over N1, P hat 2 is X2 over N2, P bar is the pooled sample proportion, and Q bar is the failure rate, essentially. So if you need to construct a confidence interval, you can set it up this way. So an E is given by this formula down here. So let's look at some examples. Alrighty. So example 1, on the article, denomination effect. So researchers report results conducted to determine whether people have different spending characteristics when they have large bills, such as $20 bills, instead of smaller bills, such as $21 bills. So they have the same amount of money, but you spend your money differently if you have a single $20 bill versus $21 bills. In one trial they conducted, 89 undergraduate business students from 2 different colleges were randomly assigned to 2 different groups. The dollar bill group, 46 subjects were given dollar bills. The quarter group, 43 subjects were given quarters. All subjects from both groups were given a choice of keeping the money or buying gum or mints. The article included the claim money in large denominations is less likely to spend the equivalent amount in many smaller denominations. To test the claim using 0.5, so there's our alpha, which means we can figure out where our rejection zone is, so on and so forth. Okay, so let's see here. So we got X1 is 12, N1 is 46, X2 is 27, N2 is 43. Okay, so our hypothesis. So our hypothesis is that the things are actually the same. So the alternate, the claim money in large denominations, that's group 1, is less likely to be spent than money in the, so there's our alternate hypothesis. Okay, so let's see here. So we need to figure out P1 hat, which is 12 over 46. We need to figure out P2 hat, which is 27 over 43. We need to figure out P bar, which is 12 plus 27 over 46 plus 43. So that's the pooled. So that'd be 39 over 89. Okay. Which means that Q bar is 50 89ths. 89 89ths minus that. Okay. So let's see here. Okay. So we need to find our test score. So Z equals, so the formula is P1 hat, so that's 12 over 46 minus P2 hat, 27 over 43, minus, now the second part here is, P1 minus P2. But we don't actually know those, but we're assuming that they are the same, which means P1 minus P2 is just going to be 0. And on the bottom, let's see here, let me get my equation sheet, is the square root of the product divided by n plus the product divided by the other n. So 39 over 89 times 50 over 89 divided by 46 plus 39 over 89 times 50 over 89 divided by 43. So this can be fun to type in the calculator, but we'll get it done. All right. So we got a fraction, we got quantity, we got 12 over 46 minus 27 over 43 minus 0 on top. On the bottom, we got the square root of a fraction of 39 over 89 times 50 over 89, all divided by 46, plus another fraction, 39 over 89 times 50 over 89, all over 43. So there you go. It's all typed in my calculator. So that gives me a z-score of negative 3.49. So that's my value. So since we've got a less than, we've got a one tail. So our rejection region is down here. So for a one tail, alpha 0.5, this is negative 1.645. You can look that up in the d-table. My z-score that I'm testing is negative 3.49, and that definitely is less than that. So we reject H0, which means the spending habit to claim money in large denominations is less likely. So they are not equivalent, which means this one is the accepted one. So we reject the null hypothesis. All right, using the data given example 1, construct a 90% confidence interval, estimate the difference between the, okay, so we're doing a confidence interval now. So we need to figure out the value for E. So here's the formula. E is Z alpha over 2, square root, P1 hat, Q1 hat over N1 plus P2 hat, Q, 2 hat over N2. Okay, so we know most of those numbers already. Our Z value is 1.645. So 1.645 square root. P1 hat was 12 over 46. So Q1 hat is the other. If 12 over 46 were successful, that means that 34 out of 46 were not, and there are 46 people in the first group. And then plus, so this is going to be 27 over 43. So if there are 27 successes out of 43, that means 16 failures. And there are 43 here. So this gives me my error. And if we math all this out, I don't really want to type it out, so I've already worked it out. 0.161. So our confidence interval is given by right here. So it's the difference P1 minus P2 minus E. Okay, so P1 is 12 over 46 minus E1, which is 27 over 43, minus the error value, 0.161. So we get negative 0.528 P1 minus P2. And then over here we got plus E, so 12 over 46 minus 27 over 43 plus 0.161. So negative 0.206. So there's my 90% confidence interval. Now, since the difference between the two population proportions doesn't include 0, it means that the two proportions are likely different. And P2 is more than P1 because these numbers are negative, which means the group in the second population is more likely to spend than the group in the first population, which is essentially what we had in the problem. Money in large denominations is less likely, so P1 is less than P2. That's the only way to get negative bounds here. Okay, and that brings us to the end of the section.